the S is being attracted by the body of mass M, and then also the body of mass M is being attracted. So these regions we call the gravitational field. So the regions where there's attractions we call the gravitational field. Gravitational field. So simply the gravitational fields means that the regions where there is force of attractions, because sometimes if these two bodies are far apart, it means that there's a great distance between them. So then we say that the body of mass M is outside the space. We call it the outside of gravitational field. So this is the gravitational field. So for instance, if this is the end of gravitational field of the S, for instance, this is the circular ends of the gravitational field of the S, for instance, we say in case you have a body at this point, this mass 2, so this body will be outside of gravitational field of the S. So that's the meaning of of gravitational field. So these are the regions where we experience the force of attraction. Okay. So that's the point that you have to remember every time. Again, we have another term which is very important. We call it gravitational field strength. Say, gravitational field strength. Gravitational field strength. It's not a gravitational field. We call it gravitational field strength. It's one of the regions in the gravitational field. So this terminology now we call it gravitational field. Gravitational field strength. Gravitational field strength, right? Gravitational field strength. So the basic question is, what is gravitational? What is gravitational field strength? Because in some of the questions they will ask to differentiate between gravitational field and gravitational field strength. So some of the questions they might ask you, so you should know the difference between them. So gravitational field, we say that this is a field strength is a ratio of gravitational force to the mass of the body in gravitational field regions. So simply say that gravitational field strength is a ratio, is a mathematical relationship, is a ratio of what? Of gravitational, is a ratio of gravitational, so it's a ratio of gravitational force of attractions we mean, right, to the mass of the body within the gravitational in the gravitational field region, or gravitational field region. Gravitational field region. So we say that gravitational field strength is a ratio of gravitational force to the mass of 40 of the body within gravitational field region. So mathematically, before even mathematically, I should give you the notations of gravitational field strength. Very important because you'll find a similar term in electrostatic, but there we call it electric field strength. This we call it gravitational field strength. In electrostatic, I will teach you about electric field strength. Okay, so there is a synonym between them. So as I told you that there's a similarities or there's a comparisons between gravitational force, nuclear force, and electrostatic force. So remember those terms. In lecture 1, I told you about that. So we say that the gravitational field strength is the vector quantity. So this is the vector quantity. It's a vector quantity that has notation of this. This is the notation for gravitational field strength. So mathematical definition, or mathematically, we define that gravitational field strength is equal to the force of attractions or gravitational force of a mass of the body. The mass of the body. Okay? So this mathematical definition that it depends, we can define different ways. Some of the books use the notations of E or use the notations of U. So we say that, because this is the vector quantity, we say, before even we go for the SI unit, so first we say that, for instance, the force of attractions between the two bodies, this is mass 1 times mass 2 times universal gravitational constant, and then radius is square. So we say that the gravitational field strength, okay, gravitational field strength, let's say r square, radius of the S square, on the S surface will be the ratio of the force, which is mass 1 times mass 2 times universal gravitational constant, and then divided by mass 1, for instance, and then radius of the S square. So this and this will cancel. So simply we find that is mass 1 times universal gravitational constant, and then the radius of the S square. So that's the formula for gravitational field strength. Remember that the force also is a vector quantity. So vectorially we can write that gravitational field strength is equal to the ratio of the force of the vector quantity, mass the scalar quantity, and then suppose that this is, let's say, mass of the S, universal gravitational constant, radius of the S square. So again, the SI unity can be asked to find the dimensions of gravitational field strength, but it's very simple because you have the formula. The SI unity of gravitational field strength is what? Is Newton per kilogram. So this is the SI unit. Because Newton is the unit for the force, and then kilograms is the unit for the mass. So that is in case that maybe on the S surface. Also gravitational field strength above the S surface, okay, can be measured as what? As a force above the S surface, force of attraction of a mass, for example, mass of the satellites. And then this will be mass of the S times universal gravitational constant. Then here we have radius of the S plus the height above the S surface square. So this is above the surface. So above the S surface. S surface. So you say that this one is equal to mass of the S, gravitational constant, radius of the S plus h, n squared, or Yes. So just that you want to find the scalar quantity, you can find the absolute values like this. Okay, so that's all about the introductions of gravitational field strengths. So we say that in astronomy or in the space flight, sometimes physicists want to bring the satellite from the infinity outside of the space of the Earth's surface to a certain point, let's say near to the Earth's surface, but above the Earth's surface. So we have to think about the work done required, because you know that we say that work done is a product of the force times sorting distance. So we say that suppose this is the point that, suppose that this is the Earth's surface, and then we have, or maybe the physicists have used a rocket that has been carrying the satellites maybe outside of the space. So if the satellite is traveling or is managing to traveling to the outside of the space, it's just like in atomic structure. We say that if electrons move from the ground level to the infinity regions, we call it the outside of the space of the nuclear attractive force, then the electrons will be free. Similarly for the satellite, okay, because the Earth has gravitational field. So if the satellites manage to travel and cross and pass the gravitational field strengths of the Earth, then we consider that satellite has reached to the infinity region. So you have infinity region of the satellites, and then we have non-infinite regions where actually that we say the gravitational field of the Earth still reaching or still arriving on that satellites at that particular point. So now I would like to teach you, that's why that I've given you a solid foundation or solid introductions of what am I going to teach you. Now I would like to teach you how do we derive at the physicists the formula to find or that will help us to know the work done required to take a satellite or to take a, mostly we talk about satellite, take a satellite from the regions or from the regions where there's no Earth's gravitational field to the regions where there's a gravitational field. Remember, the regions where there's no gravitational field, we call it infinity region. And the regions where there's a gravitational field, then we call it gravitational field region, right? So I think that before even I teach you about that issue of the work done, we say that the region whereby the gravitational field exists is called the gravitational field region. Gravitational field region. Gravitational field region. Then you say that the region whereby the gravitational field does not act is called the infinity region. Infinity region. So after go through that fundamental or foundation or solid foundational introduction, now I can teach you about the mathematical way of thinking. So the derivation of the work done of doing. So we say that the derivation. So let us go derivation of work done. Derivation of the work done. Derivation of the formula. Derivation of the formula of work done. Derivation of the formula of work done ratio of the formula of work done of bringing the satellite from infinity to the point, from infinity to the point, or in small bracket from infinity to the distance r. So the fundamental definitions of work done still the same. Work done is a product of force and distance moved in. So we'll be following steps. So that the work done required of bringing a satellite from the infinity to the point, we say the first step, we say consider, we speak physics, more mathematical, consider the figure below. Consider the figure below. So consider the figure below, which I'll be drawing for you, whereby the satellite of mass m is brought from infinity, when you say infinity, for this case it would be to the certain point equal to point C. Okay? So you say that 20 So you say that the point T from point B, infinity is B, and the point is C, point is A to point A. Okay, point A. So that's the target, to bring the satellites to point A. So then we say that, suppose that this the S is surface. Look carefully and listen, even if you stop writing first, listen carefully, because if you don't understand this figure, you'll get confusion. This is the mass of the S, and then here we have radius of the S, and then suppose that this is a gravitational field region, okay, of the S that the point used to end. And suppose that we have a satellite at infinity. So satellites at infinity, so this is the satellite of mass m at point B. Then here we have a straight line like this. So consider our intentions. We want to bring this satellite from point B to point A. Okay? From point B to point A. And then this is the center of the S. So here, suppose that we have a distance from the center to this point where we want to bring the satellite, okay? Okay, so this distance we call the x. And then against that, yes, so this is the radius of the S. I've already defined that the radius of the S is from here to here. So the distance is x. And then we say that if the distance is the distance is r, sorry. So this distance is r, the proper abbreviation. This distance is R. And then again we have total distance from point B to the center of the S. Means from the center of the satellite to the center of the S, and this point we call it, or this distance we call it X. So this is S's surface. This is S's surface. And this is gravitational S's gravitational field. Field. This is the center of the S. This is the mass of the S. Mass of the S. And then distance from here to here to the radius of the S. Distance from O to A it is R. Distance from O to B it is what is X. So then we want our intention, we want to derive a formula that will help us to calculate the work done that required to bring a satellite or any body, an heavenly body, a satellite, from the point B, which is outside of the space or away from, far away from gravitational field of the S, to point A. So then the next step we say that, so we say that this is the second step. So the second step we say that consider the satellite of mass M that is traveling from point B to point C. So because we are computing or want to write a formula for the satellites to be taken from point B to point A, sometimes that it's a lot of joules that required to remove the satellite from point B to point A. So in physics, we don't need to deal with the, it means that with how we can compute the work done for the entire or for the whole distance from B to A. We just need a small portion. We need to derive the formula for the small portion. Then we apply the concepts of integration in order to find the integration, and then we find the total work done required to move a satellite from point B to point A. So that's what I say, that consider the satellites of mass M that is traveling from point B to point C. It means that at the distance, what we mean is at the distance called dx, small change in x. Remember that dx is equal to small change in x. So as a small change in x, this is just a small distance we want to compute, want to derive. Then we use the concept of integration. We'll be integrating from infinity to the point A. So remember that this one in physics and also in mathematics, infinity we write is this symbol. So we go for the third step. The third step we say that they call the general formula of what? Of work done. So we say, since our ordinary education, we say that work done is equal to force times distance. So for this case, work done, small change in work done, which we call T, small change in work done, listen careful, stop writing if you're writing, listen careful, small change in work done, I say listen careful, stop writing if you're writing, okay, so if you'll keep on writing, okay fine, but I know I'll leave you somewhere. So small change in work done is equal to force of attraction times small change in distance, which is delta x. So to get a small amount of work done that required to remove a satellite from point B to point C, then I have to take the force of attraction between the satellites at this point, or between the satellites at this point and this point, but when the satellite is here, point B, and then when the satellite is at point C. So hence I have multiplied with the small distance that is being traveled, small distance. So for example, the satellite was here, and then it's moved just a small distance like this. So this is point B, this is point C. So if that's the case, then we say that this in physics we represent this delta, we replace it with D, the work done, and then this one also, we say that the force of attraction, this is dx. So we say that small change in work done, keep on watching, listen careful, is equal to force of attraction. So what the force of attraction? The force of attraction is equal to the mass of the satellite, because the satellite is still attracting with the S. So mass of the satellite, that's mass of the S, universal gravitational constant, and then we have what? We have the radius, or the mean distance, which is x. X is the distance from point B to point O. So then we have to multiply with a small distance that has been moved, which is called dx. So that's very important mathematical relationship. Work done. This is equal to the mass of the satellite, mass of the S, universal gravitational constant, x squared, the x. This is one of the equations. Then go for the first step. After having the formula now, the general formula of the small amount of work done that required to bring a satellite just to move few angstroms or few nanometers, right? And then we say that we got the first step. We have to apply integration to both sides. So to apply integration to both sides, on this, on the left hand side, you have small change in work done, which is the integral from where? You're taking a satellite from infinity to the A, point A. So from infinity, point A. The distance from center of the S to, listen careful, the distance from S to the point A is R. This is equal to what? Integral from infinity to R. And then you have mass of the satellite, mass of the S, universal gravitational constant, then x squared dx. So this now is a very beautiful mathematical expression. Okay? So if that's the case, we say that for this case, so we have to go the 50th step. The 50th step, we say that integrate. I will be helping you to integrate this slowly. Maybe you don't have a good fundamental or clear understanding on basic applied mathematics or calculus. So integrate the left hand side. So to integrate the left hand side, we say that we have integral from infinity to R, then d work done, So this is equivalent to say that integral from infinity to R, and then we have work done power 0, which is equal to 1, times d what? The work done. So if that's the case, we have work done power 0, and then times our variable of the differentiation, then we say that from the standard integral, that from a, which is a to b, x power n dx, this is equal to x power n plus 1, and then divided by n plus 1, and then we have our lower limit, which is a, upper limit is b. So we say that integral from infinity to r of work done at one of the physical quantity power 0, the work done. This is equal to what? Our n here is equal to 0, so we say that we have work done power 0 plus 1 over work done, no, over 0 plus 1, or limits from infinity to r. So if you find the value there, the answer is work done. So on the left hand side, if you integrate the work done, we get the work done. And hence we have to recall what you have on right hand side. We have infinity to r. This is mass of the satellite, mass of the S, universal gravitational constant x squared dx. Be careful in this derivation. Be careful once again in this derivation. So mass of the satellites and mass of the S and universal gravitational constant, all the three physical quantities are constant, so we can take them out of integral. So this is the sixth step of this derivation. We say that now integrate right hand side. So you say that the work done is equal to mass of the satellite, mass of the S, gravitational constant, then from infinity to r, then the x over x squared. So then we say that from the laws of basic applied mathematics or basic calculus, we say that this is integral from infinity to r. Then we have what? We have x or negative 2 dx. Now listen careful. Okay. Work done is equal to mass of the satellite, mass of the S, universal gravitational constant, and hence from the power that I have shown you here. Our n is negative 2, so it will be x or negative 2 plus 1. Then n is negative 2 plus 1 from infinity to r. Then what happens? So we say that the work done required to remove the satellite will be mass of the satellite, it's mass of the S, universal gravitational constant, then x power negative 1 over negative 1. Do you enjoy the beauty of physics? That is all about gravitational potential. Very interesting subtopic of gravitation. You enjoy it? Tell me in the comment section. You're watching this program from which region or which district or which village or which what. So then if that the case, you have negative mass of the satellite, mass of the S, universal gravitational constant, then you have x power negative 1, this is equivalent to 1 over x. So work done, bring the satellite now is equal to mass of the satellite, mass of the S, universal gravitational constant over x. So that's the formula for the work done required to bring the satellite from the infinity to the point. So the general formula that is required to determine the work done on bringing the satellite from infinity to the point. The point. is given as work done is equal to negative mass of the satellite, mass of the S, universal gravitational constant, and this distance, if it is r, then say over r.